Hi guys and girls, a video here on creating exponential models. My previous video was about using exponential models and finding out things about elements of the population, but this time, what if you are kind of missing a few more bits of information, or that kind of thing. So the first little bit you need to know is that if you've got an exponential thing going on, it's going to look like this. Alright, so K is usually your initial boundary of whatever it might be. B is going to be the rate at which it's increasing, and X is over what kind of time frame. And it follows that if you log both sides, then you're going to get log of K plus X log of V. And if you're not sure why that is, I recommend you go back and have a look at some rules for logarithms. So this is an equation of a straight line, and the gradient of that line is log B. If you think back to y equals mx plus c, the coefficient of x is the gradient, and the y-intercept is log k. And this is all done in log base 10. Okay, let's go with, again I've got two examples. One's a kind of scenario based, one's a bit more kind of pick out the information. So we've got a radioactive material. So a radioactive material decays so that, and then we are given the mass is a multiple of b to the t. I can use k if you want. I might as well keep that as a k. It can be any letter. M is in grams, so we're talking about the mass of something, and T is in seconds. Okay, and it is asking us to take readings and plot graphs the line of best fit. Okay, I've read that wrong. So you're given that log of M is 1.3 minus 1.8t. Okay, and it's asking us to find K, because I changed it from a K, a C even, and B. Okay, so we've got, this is basically the line of best fit for the readings, because we've got an equation of a straight line here. So it's taken a load of readings about this radioactive material, and it's going like this, and the line of best fit is this here. And that's the kind of gist of the question. And it's saying, okay, well, if we know the equation of the line, can we work backwards and find what we started with? Yep, absolutely we can. So, if we know, oops, there we go. I'm completely messing this up. There we go. So we know that if we take the y-intercept, we know that log of k has to be equal to 1.3. And we know that log of b has to be equal to negative 1.8. Alright, so all I've done is said, well, the gradient, log b, is equal to negative 1.8, and log k is equal to 1.3. So I'm just matching up the parts of the equation. Now I'm going to have to solve them. So what undoes a log? Well, it's to raise it, so 10 to the power of k. of the 10 to the power of log k, because we're in log base 10, and 10 to the power of 1.3. So the log and the 10 cancel, giving me k. It's 10 to the power of 1.3, which is approximately 20. Same here, so 10 to the power of log base b, or log of b even, and 10 to the 0. Ugh, oh my word, what is with my words today? They're going to cancel out to give you b. So b is approximately 0.016. There you go, done. It's matching up parts of an equation. Okay, so let's have a look at another example. So we've got a line has gradient 2.6 and y-intercept negative 0.9. And we're told that y equals ax to the n. It's a slightly different form, but it's still exponential because we're all trying to find a and n. Okay. So if we log it, so log of y, log of a, in log x. Alright, so the x is in a slightly different position. Okay, don't worry, it'll get there. Wait, if you just heard that weird noise, that was my cat. I don't think she'll believe we'll get there, but we will. We will. Okay, right, where do we go to? So this here is our y-intercept. So negative 0.9 is log of a. We can do the same thing that we did before, so raise it. So 10 to the negative 0.9 is a. So that is approximately 0.13. And we need to know the gradient. Now, what part of that do you think is the gradient? It's the n. Right, it's the number in front of the x, even if it's logged, it doesn't make any difference. So n is 2.6. I don't think anyone's convinced of that, but I promise you it is. Okay, anyway, it's an unusual form, that one. Most of the time you're going to have your x in your power, because that's what, or your t, you know, whatever it is, in your power, because that's what makes it traditionally exponential. But if you think of 2 to the, excuse me, hiccups, 2 to the n or 3 to the n, they're still exponential. They're fine, they're still exponential. So it doesn't have to be in the power. Okay. Hopefully that made sense. Again, it's just matching up pieces of an equation with the information that you are given. The important thing, as always, is this bit up the top here. That bit there. Ooh, there you go. That bit there that I've half drawn through, that's your important bit. Anywho, see you later. Bye!